The three factors that determine the type of work a motor can produce are speed, torque, and horsepower. Speed is defined as how fast the motor performs its work. For example, a shaft can rotate slowly or quickly. The typical units of measurement for rotational motor speed are revolutions per minute, or RPM. Work is defined as a force applied over a distance. In the case of flywheels, winches, and motors, the work is called torque. Torque is a special type of work that produces rotation. Torque occurs when a force acts on a radius. Typical units of measurement for torque are pound-foot. The torque illustrated here is equal to 1 pound-foot. Horsepower is defined as the rate at which work is accomplished. Years ago, before motors were invented, most work was accomplished manually. It was estimated that one horse could accomplish approximately 33,000 pound-foot of work per minute, and thus the term horsepower was born. In modern terms, horsepower is simply another unit of measurement for power and can be translated into watts, BTUs, joules, or any unit of power. Units that measure motor power are typically in horsepower or watts. You can manipulate the connection among speed, torque, and horsepower by understanding how they are related. The work accomplished here, the torque, is represented by the weight moving along the conveyor. If torque remains constant, speed and horsepower are proportional. As the speed, or RPM, increases, horsepower increases to maintain constant torque. If speed decreases, horsepower decreases to maintain constant torque. Let's say we wish to keep torque constant but want to increase the production of barrels. If the torque or number of barrels on the conveyor belt remains constant but speed increases, then the horsepower of the motor also increases. In other words, a more powerful motor is required to produce the same amount of torque more quickly. Similarly, the opposite is true. If we wish torque to remain constant and decrease speed, then the horsepower of the motor also decreases. If speed remains constant, then torque and horsepower are proportional. As the torque increases, horsepower also increases to maintain constant speed. As the torque decreases, horsepower also decreases to maintain constant RPM. Let's say we want production to increase, but the speed of the conveyor to remain constant. If torque increases, horsepower also increases to compensate. This means a more powerful motor is needed to produce more torque at the same speed. Similarly, the opposite is true. If we wish speed to remain constant and decrease torque, then horsepower also decreases. If horsepower remains constant, then speed and torque are inversely proportional. As the torque increases, speed decreases to maintain constant horsepower. As torque decreases, speed must increase to maintain constant horsepower. Let's say we want the horsepower of our motor to remain constant, but wish to increase the torque. If torque increases, the speed of the conveyor decreases, so that the horsepower required of the motor remains constant. Similarly, the opposite is true. If the torque decreases, the speed of the conveyor increases, and the horsepower generated by the motor remains constant. To calculate the amount of horsepower required to move a horizontal load, we must first consider the occurrence of sliding friction. Friction occurs when two materials resist moving against one another. For example, it's much easier to pull a block of metal across a smooth field of ice than it is to pull it across a rocky path. The friction between the block and the rocks is greater than the friction between metal and ice. The amount of friction generated depends primarily on the materials which are in sliding contact. The coefficient of friction, symbolized by the Greek letter mu, is a dimensionless quantity which describes the ratio of the force of the friction between two bodies and the force of them pressing together. This coefficient can be used to help determine the amount of force required to move a load horizontally across a surface. Many manufacturing handbooks contain tables that publish the coefficient of friction for common materials. The amount of force required to slide a load and overcome the surface friction is calculated by multiplying the coefficient of friction by the weight of the load. Once this force is determined, it's easy to calculate the required horsepower to move a horizontal load. First, find the horizontal force required by multiplying the coefficient of friction by the weight. Then, determine the amount of work required by multiplying the force by the distance in feet to be moved. Next, calculate the power by dividing the work by the time in minutes. Then, convert to horsepower by dividing the result by 33,000. Finally, add 5% to compensate for estimated friction losses in the motor or cylinder. Let's try an example. Assume the barrel weighs 100 pounds. The coefficient of friction between the belt and the platform is 0.3, and the barrels move 20 feet in 0.1 minutes. We can determine the horsepower required of the conveyor motor by accomplishing the following calculations. First, find the horizontal force required by multiplying the coefficient of friction by the force of the weight, which is 100 pounds. In this system, the horizontal force is 30 pounds. Then, determine the amount of work required by multiplying the force by the distance, 20 feet. For this system, the work required is 600 foot-pounds. Next, calculate the power by taking the work and dividing by the time, 0.1 minutes. The power is equal to 6,000 foot-pounds per minute. Then, convert to horsepower by dividing the result by 33,000. This yields a result of 0.18 horsepower. Finally, add 5% to compensate for estimated friction losses in the motor or cylinder. The final result is 0.19 horsepower. With this result, system designers can ensure the right size motor is available to operate the conveyor. If the distance to be traveled isn't on a horizontal surface, the angle of the surface must be taken into account. To determine the total force required, we must add the force required to raise the load to a higher elevation with the force required to overcome the friction. The total force is equal to the weight times sine A plus the weight times the coefficient of friction times cosine A. Once these two forces are combined, we can continue with the same steps used previously to calculate the size of the motor required. First, find the horizontal force required by adding the force required to raise the load to a higher elevation with the force required to overcome the friction. In this system, the horizontal force is 75.98 pounds. Then determine the amount of work required by multiplying the force by the distance, 20 feet. For this system, the work required is 1,519.6 foot-pounds. Next, calculate the power by taking the work and dividing by the time 0.1 minutes. The power is equal to 15,196 foot-pounds per minute. Then convert to horsepower by dividing the result by 33,000. This yields a result of 0.46 horsepower. Finally, add 5% to compensate for estimated friction losses in the motor or cylinder. The final result is 0.48 horsepower. With this result, system designers can ensure the right size motor is available to operate the conveyor on an incline. As expected, it takes a stronger motor to move weight up an incline than on a horizontal surface. The relationships among horsepower, speed, RPM, work, power, and force allow technicians and system designers to determine the appropriate characteristics of motors, cylinders, and other fluid system components required to operate any system.